So, as I have just said, I am Ekaitz, the Innovation Manager of Burdinola. And today I would like to present the process of development of the nanochamber, the device that you are seeing in the screen. And this is a critical equipment to keep safe the researchers in the nanotechnology field, mainly in laboratories where raw material is handled in powder state and manually, okay? So we are basically a company that performs laboratory projects, and the customers were requesting us more and more equipments to work safely with nanomaterials. So we started investigating about the topic and applying the experience that we had in the field of laboratory containment, equipments, fume hoods, biological safety cabinets, and so on. So what is the content of this presentation? First, I will try to show an example of the effects of some nanomaterials in health, just a very short example. Secondly, I'm explaining what requirements a laboratory equipment should meet to work safely with nanomaterials. And as I have said before, manually with not huge amount of material and always in powder state, okay? And having those requirements, I am proposing an equipment that is the one that I am presented today, and explain the validation of the process of the development, okay? So, as the starting point, what's the risk of nanomaterials? We usually use the example of asbestos, okay? So you can see in the picture, let me, okay. Here, sorry, let me show. Okay. Here in these pictures, you can see the structure of the asbestos in the same scale, in the nanoscale, and the structure of the nanotubes, okay? So we can see that both structures in the scale are quite similar. And in the right, you can see the penetration of the alveolar epithelium by a multi-layer carbon nanotube. So we can say in some, as you will know, the shape of all nanomaterials is different, but it's just an example that we could say that the asbestos and some nanotubes has the same structure and the effect on the health could be the same. So we can say that safety in handling nanoparticles in the laboratory is in incipient state. Why I'm saying that? Because its detection is not easy. In some cases, they have toxic effects, and they are not immediate, so it's quite complicated to detect it in a short term of time. And the most critical point is that there is no any reference standard or any specific regulation when we try to design or manufacture protection equipment. So once identifying the risk of nanomaterials, we analyze a bunch of bibliography, guidelines, recommendations, and so on, and mainly in order to find what requirements should met by a laboratory equipment. So you have there some references. If you need more references about the bibliography, you can ask for that. And we conclude that there are 5 basic requirements that protection safety equipment should comply with. So the first one is handling of nanomaterials should be performed in a closed system. Okay, mechanical ventilation and filtration are recommended for this enclosure in reference to the workers breathing zone. So in order to not contaminate, pollute the environment. And the air inside the cabinet or the enclosure should not be recirculated inside the laboratory, because there is no, for the moment, there is no 100% effective filter for nanomaterials, not ULPA, not EPA, no any filter, 100% effective, okay? And we should try to avoid any turbulence to not allow particles going out of the system. Although we have a negative pressure, we can demonstrate that turbulences can break the containment of the enclosure. So after that, we did a benchmark and analyzed the most used equipments in laboratories and check if they were committing with those requirements. So first, glove boxes. They are safe since they commit with all requirements: fully closed system, mechanical ventilation, negative pressure. The air inside the cabin should not be recirculated, so there are fully closed system, physically closed system, and they have no recirculation, but they are not very comfortable for the daily use in a laboratory, since it's based on a glove interface. So there are some actions that are repeated in the laboratory process as dosage, weighing, and dissolutions, and all of them needs to be done precisely, and gloves doesn't allow to do that. Okay, so this is a safe equipment, but not very comfortable. Okay. Regarding biosafety cabinets that are quite used in this field, they are not safety at all with nanomaterials, mainly for two reasons. The air speed is quite high, between 0.35 and 0.45, and it creates or generates turbulences. So in some cases, the contention is broken. And in CV2, where horizontal airflow is used, when the users start using this kind of equipment, broke the horizontal flow, and some turbulences could appear. So we can say that this kind of equipment is not safe. The same for the laminar flow cabinets, both vertical and horizontal, just protect the sample, but doesn't protect the user. In some cases, as I have mentioned before, the weighing process is quite used for this kind of materials. And here in the picture, you can clearly see when an horizontal flow is used, the user broke this flow, and some turbulences are generated in front of him. So we can say that the contention in those cases can be broken. And we could say the same for the fume hood. This kind of equipment is the most used for handling nanomaterials in the laboratory. And regarding the safety, it's not safe at all for the same reasons mentioned before. Okay, here we have a difference, because in these cases, the extraction is done by the upper part of the cabin. Okay, so particles, nanoparticles, or nanomaterials, in this case, try to go down by gravity, and they remain floating in this zone. So the air is pulling them up. By gravity, the particles tend to go down, and they keep in the middle position. Okay, so they remain here, and in some cases, by the use of by the user that is cutting the flux, the flow of air here, in some cases we can break the containment and the particles go out. Okay, so polluting the laboratory. Okay, so taking this analysis into consideration, we found that an equipment should be developed to work with nanomaterials in the laboratory, meeting the next requirement. Okay, we need a closed system with outdoors extraction. So I have mentioned before that there is no any filter 100% effective or efficient. So we highly recommend to do an outdoors extraction. We recommend also lower speed to avoid turbulences. The higher the speed, the higher the turbulences. The airflow should facilitate the natural movement of the particles by gravity. And of course, we need a strongly tested equipment. Okay. And of course, we also suggest a double filtering system, because we don't need just to protect the user, that is the most important, but we also have to protect the sample. So here, our proposal, okay? This is the nano chamber, and this is the technology that we have patented in order to have a safe equipment. And I will try to explain the basic ideas, okay? So first of all, we have an outdoor extraction of the air. So this is going outside the laboratory. Here is going outside. So we are not recirculating it inside to avoid any pollution, okay? The second point, we have both filtering points, one for the input air. So this way we provide a clean air inside the chamber, and also an output filter to clean the air that we are extracting outside. I have said before that there is no 100% effective, so we are cleaning here the air 90%, so 1% of the particles are going outside. But as you will know, the conglomeration of this kind of materials is done quite easy. So we are going from a nanoscale to a micro or milli scale outside due to humidity and so on. And the most important technology that makes this chamber so secure is the vertical multilaminar airflow. Okay, so you can see here with the blue arrows, there are several vertical curtains here, air curtains. We're introducing the air from the upper part and at different speed, and we are doing it both inside the chamber, okay, and outside, okay? So with these barriers, what we want to achieve is generating a barrier here, okay? So let's say that this is the user here, okay? And we generate a virtual air barrier between the user and, let's say, the sample that should be here, okay? Apart from that, there is no air exchange between the inside and the outside. So the air is coming from here, goes here, and it's going from there to the outside, and the same for the inner part of the cabin. Okay, it's done by here, and after that, it's going out. So In other cases, we have seen that the user was breaking the airflow. In this case, the airflow is not horizontal, it's done vertically, okay? And this is the basic or the basis of this technology. So we can work directly between, we can handle directly the sample using just an air barrier. And we can say that this system is safe for the user and also for the sample. So there is no air exchange between the user and inside the chamber, and the air coming is filtrated. So the sample is always with a clean air, let's say, and there is no exchange of air between the user and the inside of the chamber. So just as summary, these are the critical requirements that a nanochamber meets that are not met with other equipments. Okay, so we are using a multilaminar vertical airflow and very low air speeds, so there is no air exchange. Okay, double filtering for the sample and for the user, and quite important, the outdoor extraction. Okay, not to recirculate the air to the laboratory because we can clean it at 100%. Okay, and also important, that is strongly tested. So I have mentioned before that there is no any standard, so we have developed our own standard that I am presenting in later in some slides. Okay, so regarding the contention, what are really the requirements or the features that are related to the contention? So the multilaminar vertical airflow, low air speed, double filtering system, and outdoor extraction. So in summary, with those features, we obtain this one. So no any turbulences generated inside the chamber, so we avoid any containment break. We obtain 100% efficiency in terms of containment. I will show you later the test that we have performed. There is no sample loss without altering the physical properties of the sample. This is because we are using a very low speed and the air is clean inside, not polluted inside the chamber, and very energy efficient because due to our low air speed, we don't consume much in terms of energy compared to conventional fume. And of course, as I have mentioned, it's strongly tested. Okay. I have mentioned before that there is no any standard to test this kind of equipment. So we have developed our own test protocol, and it's based on two tests mainly. The first one based on a standard for EN 14175, that is the one used for fume hoods, and the other one, this one, the adapted test, is one adaptation of the test used for the fume hoods. And what we have done is replacing the SF6 tracer gas used in the EN 14175 by nanoparticles, NaCl nanoparticles. Okay. So in the test that we use in fume hoods, basically are two kinds of tests. The first based on injecting some SF6 gas inside the cabinet, or in this case, the nanochamber or a fume hood. So you can see here how we inject the gas inside, and we put some gas detectors outside. Okay. This is one kind of test, and the other one represented here, we are doing the same test, but we move a board in front of the equipment in order to generate some turbulences outside the system and check if the containment is broken. Okay, so we move this board in both directions. So we generate a turbulence in the front of the fume hood or the nano chamber, that is the equipment that we have tested, and check if the solution is robust. So in this case, the result is quite good. The limit for the conventional fume hood is 0.63 ppm, and here, in the worst case, we have improved that measure quite good. Okay, obtaining an 0.027 ppm detected outside in one point. Okay, but this is, as I have said before, this is the test that is usually performed to a fume hood. But in terms of equipment used for nanoparticles, it's more meaningful, this test. Okay, so we have done the same. Here we have a particle injector. We are injecting particle inside the nano chamber, and outside we have a detector of nanoparticles. So we have replaced the SF6 by nanoparticles. Okay, so the results, that I think that this is the critical part. Okay, sorry for this. Okay, there is a lot of noise here, but I will try to explain. Sorry for this. In this side, in the left side, in the upper, in this graphic, here in the time scale, we can see the detection of nanoparticles outside the nanochamber. Okay, and in the picture below, we have in dot blue line when the chamber is running. Okay, this part will be working, the nanochamber, and this part would be switched off. And in the red line, we indicate in the same time scale where we are injecting nanoparticles inside the chamber. So here we are injecting nanoparticles, and here the same. And we have performed the same test for the nanochamber and for a conventional fume hood. Okay, so if we see the results, if we have switched on the nanochamber and we start injecting nanoparticles, so this side of the graphic, we detect that there is no any particle outside. Of course, if we switch off here, if we switch off the nanochamber and inject nanoparticles, here the scale more or less is here. Okay, so we detect that there are some particles, a lot of particles outside the nanochamber. So when we have running the nanochamber, there is no contention break inside, and of course, if we switch off the nanochamber, we are not extracting air. We have a lot of particles outside. We do the same test in the right side with a conventional fume hood. Okay, so here the critical part is here. Okay, so when we are running or is operating the fume hood and we are injecting some nanoparticles inside. So here you can see that we detect a lot of nanoparticles outside the fume hood. So here we have a great contention break of the fume hood. And of course, this is a typical result. If the equipment is not running, of course, we detect a lot of particles outside because the protection system is not working. Okay, so here the difference. Here, there is 100% containment within nanochamber, and here we have a huge break of the containment with a conventional fume hood. Of course, if you need more detailed information, you can contact me, and I will be very happy of sharing all the information and all the tests that we have performed. Okay. And a summary. So what we consider the best performance to obtain 100% of efficiency, and what's the features that are quite important for an equipment to meet. First one, the laminar flow. Okay, the laminar flow is quite important to contribute to avoid any turbulent flow. So we have seen that the turbulent flow is the main reason of a break of containment. But this laminar flow needs to be vertical, okay? Because if we have an horizontal flow, the user breaks that horizontal flow. It's quite important also to use low velocities, okay? So the higher the velocity, let's say that the high velocity contributes to turbulent flows, okay? And this is quite important, extend this laminar flow to the external area. So we are using a laminar vertical flow inside and another one outside in order to generate this virtual air barrier, okay? So this is all. If you have any question, I will be very happy to answer you. And of course, here you have my contact information. If you have added information or any question apart from the one that you are doing here, I will be very pleased of sharing all the information that we have with you. Okay. So if there is any question.